In this next lesson in logic and reasoning, we will learn about conditionals and definitions. The objective of this lesson is to write biconditionals and recognize good definitions. So, what is a biconditional? A biconditional is a single true statement that combines a true conditional and its true converse. We're going to write a biconditional by joining the two parts of each conditional with the phrase if and only if. And you can abbreviate that IFF for if and only if. So a biconditional combines if P then Q and if Q then P, and it combines that together to be, and you write it P with an arrow going both ways, a Q, and you read that P if and only if Q. You can rewrite a biconditional as two conditionals that are converses. So let's look at problem 1 to use this. So in problem 1, we're going to write a biconditional. So to write a biconditional, you have a conditional statement and you write its converse. So if the converse is also true, then it can be written as a biconditional. So that condition has to be true. The conditional statement has to be true and its converse has to be true before you can write it as a biconditional. So here, this conditional statement states that if the sum of the measures of two angles is 90, then the angles are complementary. So that is a true statement. And we're going to look at its converse. The converse is going to say something like, if two angles are complementary, then the sum of their measures is 90. So all we did for the converse is we switched or exchanged the hypothesis and the conclusion. That is also a true statement. So the conditional is true, the converse is true, so we can write it as a biconditional. So to write it as a biconditional, go back to the original conditional statement that says if the sum of the measures of two angles is 90, then the angles are complementary. And we're going to take out the if and take out the then, and we're going to replace the then with if and only if. So let's rewrite that. The sum of the measures of two angles is 90 degrees if and only if the angles are complementary. In problem 2, we're going to identify conditionals in biconditionals. So we're going to start with a biconditional this time and then identify the conditional and its converse that it came from. So what are the two conditional statements that form this biconditional? The biconditional states that two numbers are additive inverses if and only if their sum is 0. You know it's a biconditional because it contains the words if and only if. So let's dissect this into its parts. The hypothesis of this statement is that two numbers are additive inverses. And the Q part, the conclusion, is that their sum is 0. So you might need to refresh your memory on what an additive inverse is. Additive inverses are numbers like a positive 2 and a negative 2. They add together, and their sum is 0. So now let's look at the conditional statement that can be made from this. If P, then Q is the conditional, and we're just going to take these two, the hypothesis and conclusion, put in an if and a then, and create the conditional statement. So if two numbers are additive inverses, then state the conclusion, their sum is 0. And that is a true statement. So now let's look at the converse of that, which means we're going to take the hypothesis and conclusion and exchange them and write it as an if-then statement. So to do that, we would say if their sum is 0, then two numbers are additive inverses. Which is also a true statement, which is why they could be written as a biconditional. So next, let's look at a good definition and what needs to be true for a definition to be considered a good definition. To be a good definition, it uses clearly defined terms. It is precise, and it is reversible. It can be written, in other words, as a true biconditional if it's reversible. So let's look at problem 3 and writing a definition as a biconditional. So in problem 3, it says, is this definition of an equilateral triangle reversible? So an equilateral triangle, just as a review, an equilateral triangle is a triangle that all of the sides are congruent and all of the angles are congruent by definition. So we're going to see if this is if this definition of an equilateral triangle is reversible. If it is, then we're going to write it as a true biconditional. So here's the definition. The definition says an equilateral triangle is a triangle with 3 congruent sides. So let's write this as a conditional statement. So we're going to write it as an if-then statement. So one way we can do this is if a triangle is equilateral, then it has 3 congruent sides. Now let's write the converse of that, which means we're going to switch the hypothesis and the conclusion. The converse is going to say if a triangle has 3 sides, 3 congruent sides, then it is equilateral. So your next question is, are both the conditional and the converse true? The answer is yes, both of those statements are true. So if it's yes, then the definition is reversible. And you can write the conditional and its converse as a true biconditional. So let's take that and write it as a biconditional. It would say a triangle is equilateral if and only if it has 3 congruent sides. So now let's look at problem 4. Problem 4 is over on the bottom of the left part of your page. It's identifying a good definition. Which of the following is a good definition, and explain why or why not? The first one, A, says dogs are animals with 4 paws. That one is not a good definition. Why not? You can give any number of counterexamples of animals with 4 paws that aren't dogs, like cats. Cats have 4 paws, but they're not dogs. Squares have 4 sides is the next one. That's also not a good definition, because a rectangle is an example of a figure with 4 sides. It's not a square. C says Tuesday is the day before Wednesday. That one is a good definition, because there is no other day of the week before Wednesday is the day of the week before Wednesday. So that one is the best definition and a good definition. And because you can't find a counterexample of anything that is the day before Wednesday. The last one, just to look at it, an acute angle has a small measure. That one's not a good definition, because that one is relative and vague as to what is a small measure relative to what other angle that could be a large angle. It could still be obtuse and be smaller than a straight angle, for instance. So those, so C is the best answer there for the good definition.